Okay, so welcome back. Today we're going to take a look at trigonometric functions of acute angles. I have a new app on my iPad that I'm recording this with, so excuse me if it gets a little glitchy. I'm still learning it. It's called Explain Everything, so I'm testing it out. We're going to start here with a nice drawing of a right triangle, and notice that notice you've got your terminal side in quadrant 1. I'm just going to redraw it over here. You have, let's call this angle A right here in standard position. There's your terminal side. We are looking at acute angle A, and we are remembering that sine of A is equal to y over r by definition, but now we're also calling that opposite over hypotenuse. So for some time I've been talking about Sohcahtoa. Now you're really going to see this acronym come to life. So for simplicity, let's go ahead and put a point there on the terminal side, and namely that point is going to be xy. We're going to call that point xy. Let's drop a little right triangle right there. Okay, then you know the distance from here to here is x, and the distance from here to here is y. Okay, and you can see that from this drawing here as well. We deemed the radius little r, so we'll call little r the radius of rotation from here to here. So that just means that if I were to, take a compass and swipe out a circle of radius r, that's would be the distance there. Okay, now let's practice getting comfortable with Sohcahtoa, with the fact that sine is the ratio of opposite over hypotenuse. So side opposite of A, so I'm going to draw this in another color. If you're standing here at A, who's opposite of A? And y, and then what's the hypotenuse of the triangle? R. See, so y over r means the same thing as opposite over hypotenuse. Cosine is x over r, and I'll do this in another color. X over r. But notice that x is the adjacent side to A, and again r is the hypotenuse. So what I'm getting at is x over r means the same thing as adjacent over hypotenuse, and y over x means the same thing as opposite over adjacent. Hence Sohcahtoa, the acronym that helps you remember. S for sine, sine is a ratio of opposite over hypotenuse. C for cosine, adjacent over hypotenuse. T for tangent, opposite over adjacent. So let's just really practice using our Sohcahtoa. Let's see if it'll let me move this up here. Okay, so here we have a triangle, and it says find the sine and cosine and tangent for angles A and B. Well, let's just start, put your eyeball situated here at A. Well, we know that sine of A is opposite over hypotenuse. Well, who's opposite of A? Aha, 7. And who's the hypotenuse? 25. Let's keep practicing. Now we know that cosine of A is adjacent over hypotenuse. So hopefully you're thinking 24 over 25. And if you like, you can hit pause and, and see if you can beat me to the punch, and then check your answers with me. Tangent, opposite over adjacent. So remember, opposite is 7, adjacent is 24. Okay. Now, also remember that if we wanted to find, cosecant, secant, and cotangent, those are just reciprocals of the first three, respectively. Okay. Now let's scoot that down a little bit. It also said it's neat the way it moves it around like that. This is my new toy, so I'm really excited to try this app out. It also said to find the sine, cosine, and tangent values for angle B as well. So let's practice that, situating ourselves at angle B. So I guess I'll pull another color. Here's angle B. So what is opposite of angle B? 24, right? So that means that sine of B would be equal to opposite over hypotenuse, so 24 over 25. Cosine of B would be equal to adjacent over hypotenuse, which would be 7 over 25. And tangent of angle B, that should say tan, tangent of angle B would be equal to opposite over adjacent. So 24 over 7. All right, hope that helps. Now, let's scoot that down a little bit, see what's next. Cofunction identities. Okay, now these can be a little bit tricky to explain to someone, so I'm just going to kind of start off real easy. Pick an angle, any angle, that is less than 90 degrees. Okay, 35. So you agree that if I have 35 degrees, you agree that you could tell me the complement of 35 degrees pretty easily, right? So complementary angles add up to 90, right? So maybe you're thinking 55 degrees is its complement. So for any acute angle A, cofunction values of complementary angles are equal. So you just have to first check that you have complementary angles, and then you know that their cofunctions evaluated at those complementary angles will be equal. So what does this mean? Think of sine. This means that sine of 35 has to be equal to, well, what's the cofunction of sine? Cosine. So that means that would have to be equal to cosine of 55 degrees. So what I'm getting at is, notice that 35 and 55 are complementary, and also notice that sine and cosine are cofunctions of one another. So that's pretty much what this box is saying. Let's play with it until you start to catch it. Write each function in terms of its cofunction. So let's just start here. What is the cofunction for cosine? Sine. It's kind of a way of saying, think about it like this, sine, and then if you stick the word co in front of it, cosine. So it's kind of like sticking the word co in front of it. It means cofunction. Okay, it's like a tangent, right? Now stick the word co in front of it, cotangent. That's all it means. So when we talk about cofunctions, we're talking about a function, and then if you put the word co in front of it, that's its cofunction. Okay? So cosine of 52 has to be equal to sine of what? Well, we know they got to be complementary, so whatever 90 minus 52 is, which is 38. Okay? And again, you shouldn't just believe it. In fact, I'll do this with you on my handheld. Don't just believe that this is true. Verify. Verify on your calculator. Ready? Hit cosine of 52 degrees. Make sure you're in degrees on your calculator. And calculator is going to spit out 0.616, right? Rounded. So then go ahead and hit sine of 38 degrees on your calculator. And guess what? Spits out the same decimal equivalent. See? So you know you've done it right if you verify it. Note to self, verify on calculator. All right. Let's scoot that on down. Tangent of 71. Well, the cofunction for tangent is cotangent. And then, after we get that, then we say, well, what's the complement of 71? 19 degrees. Good, let's keep playing. Secant. Well, what's the cofunction for secant? Cosecant. Right? And then you ask yourself, and what's the complement for 24? So whatever 90 minus 24 is, which is 66. And again, all of these things you could easily verify on the calculator. Okay? So when you first read these magical boxes in the book that talk about cofunction identities and things like that, at first they look difficult, but when you realize what they're just saying a function and its cofunction will be equal when the arguments add up to 90 degrees, when the arguments are complementary. That's all it's saying. Okay, let's scoot that on down. So that enables us to solve something like this. Matter of fact, you know what? I'll give us a little room. I'll scoot this on over. It says find one solution for the equation. Now there's infinitely many solutions, obviously, because you can look at coterminal angles, but find one solution for the equation and assume all angles involved are acute angles. So, all right, well, the only thing that's going to allow us, I'm going to write it bigger over here, we're looking for when does cosine of theta plus 4 equal to sine of 3 theta plus 2. The only thing that will allow us to, equate those two, given, that you see that they are cofunctions. So the first thing you see is that they're cofunctions. The next thing that triggers in your mind, if they're equal and they're cofunctions, you know that their arguments have to be complementary. So you know that theta plus 4 plus 3 theta plus 2 has to be 90. And boom, that's your setup. Then you just use algebra to solve that from there. So theta and 3 theta makes 4 theta. 4 plus 2 is 6. And you can just go ahead and solve that on out. So now you know 4 theta equals 84. So we eventually arrive at 4 theta equals 84. Therefore, theta is 21. But here's the catch. You definitely want to throw that back in. So this will be true when theta equals 21, but you want to, throw that back in and verify. What do I mean by that? Well, 21 plus 4 is 25. So, is it true that cosine of 25 degrees is equal to, now take that 21 and throw it right there. Well, 21 times 3 is what? 63 plus 2 is 65. So it's equal to sine of 65. And one thing we're seeing that's good is, hey, 65 and 25, those are definitely complementary. So it's working out. And you could clearly type it on your calculator and verify that as well. Okay? All right, hope that helps. Let's scoot that on down. Well, I guess we're on the next slide already. I don't see anything else on that. All right. Now we begin, in future lessons we're going to be talking about the unit circle, but in order to design our own unit circle, we have to look at some basic constructions of 30, 60, 90 triangles, two very popular triangles, the 45, 45 right triangle and the 30, 60, 90 triangle. So let's just start with an easy construction for all of us to do. So just take, an equilateral triangle. So think about it like this, equilateral, 60 degrees, that means all these angles here are 60 degrees, right? Go ahead and bisect that first 60 degree angle, so then you're going to have 30 and 30, right? So you're going to end up with here. And then it's like after you bisect it, take away this triangle right here. And what would you have? Well, you'd have yourself a 30, 60, 90 right triangle. Here would be 30, here would be 60. But, for simplicity, that first equilateral triangle, let it be 2, 2, and 2, on all sides. So think about it like this. If you take away then this side after you've bisected your angle, then from here to here is going to be 1. Okay? Then we keep thinking about it a little bit. So if this side is 1, and if the hypotenuse is 2, then what's this long leg right here? So this is 1. This is 2. What is it from here all the way up to here? Well, you can go off on the side and figure that. 1 squared plus something squared equals 2 squared. And you can solve that out. So something squared will eventually equal 4 minus 1, which is 3. So therefore, eventually you'll figure on that being the square root of 3. Okay? So once you know that the distance from here to here is the square root of 3, it's going to be really easy for you to start finding sine, cosine, and tangent of a 30, 60, 90 triangle. So let's zoom in here a little bit. Let me redraw this triangle. So if this is 60, and if this is 30, and if this is 90, and now we just figured on this being 1, 2, and root 3. And again, I just started with this simple construction of an equilateral triangle just because you want to pick easy numbers to start off with. The ratios are going to remain the same despite how large the numbers are, so just pick these easy numbers for starters. Okay, now we know Sohcahtoa, so let's take a look. All right, so sine of a 30-degree angle, let's put our eyeball here at the 30 degree, is opposite over hypotenuse. What's opposite of 30? 1, and the hypotenuse of that right triangle is 2. All right, then cosine of 30 is adjacent over hypotenuse. Adjacent over hypotenuse. And tangent of 30 is opposite over adjacent. So 1 over root 3, which you clearly have to rationalize, so you would end up with root 3 over 3. Okay? Multiply the top and bottom by square root of 3. And I think you guys are getting good at rationalization by now. So we can practice finding sine, cosine, and tangent for 30-degree angles and 60-degree angles respectively. So I'll hit pause as we practice with the 60-degree angle. Okay, so all I'm going to do is keep stealing this lovely right triangle here and just kind of putting my eyeball at different locations. So here's the 30, the 60, here's the 1, the 2, the root 3. Okay, now I just want to practice getting sine of the 60-degree angle. Well, if I'm here at 60, then opposite over hypotenuse. Okay, cosine of 60, adjacent over hypotenuse. And tangent of 60, opposite over adjacent. So root 3 over adjacent, which is 1. Or you could just say root 3. Okay? All right, hope that helps. Now another very, clearly, again, if we have sine, cosine, and tangent of 60 degrees, they're reciprocals. We could easily generate cosecant, secant, and cotangent. Another famous one, the 45-45 right triangle. So for simplicity, just all you do is start with a square. Something that you always start with something that you know in math, like when you're trying to derive. Start with a square of equal sides, 1, 1, and use these nice easy numbers, 1. Well, if we bisect this angle here, then here's our 90, and then this would be 45, and this would be 45, right? And it's like we're going to take this piece off and just focus in only on this triangle, which is in essence what's drawn here, okay? Now if this leg's 1 and this leg's 1, you know, how do you figure on the hypotenuse? Well, 1 squared, now you know that. 1 squared plus 1 squared equals hypotenuse squared. So therefore 2 equals hypotenuse squared, so the hypotenuse must be the square root of 2. Now once you've laid that construction, you're ready. You're ready for what? To do your sine, cosine, and tangent. Now see, I'm going to go off on the side again just so I can think about that. So 1, 1, you know, here's 45 degrees, here's root 2. And now we can start to think, all right, well, what's sine of 45 degrees? Well, opposite over hypotenuse. So opposite, here's my 45-degree angle, opposite over hypotenuse. But clearly I have to rationalize that, so eventually I'd end up with root 2 over 2. Okay, now I'm under the general assumption you know how to rationalize that by now because we've been doing that. Cosine of 45 degrees is adjacent over hypotenuse. Well, hey, that's the same thing, 1 over root 2. So root 2 over 2. And then tangent of 45 degrees, if you're just looking at this triangle, is, you know, opposite over adjacent, which is, adjacent is this piece right here. So 1 over 1, which is just 1. So hence, after all that sweat equity, what you've in essence done, and you see these in textbooks all the time, is these lovely tables. But it's kind of like, and students often think they have to devote these tables to memory, which does help you gain speed. But now we see where they came from. So, you know, sine of a 45-degree angle is root 2 over 2. Well, we just figured that out, you know. And cosine of a 45-degree angle is root 2 over 2. And tangent of a 45-degree angle is 1. So, you know, we just did the construction ourselves and figured that out. So, you know, like I said, don't feel like you have to memorize these tables. You could always resort back to the basic construction of the 30, 60, 90 triangle and the 45, 45 right triangle that we just did. Okay, let's see. Let's scoot that on down. Oh, and that's as far as we had to get for today. Okay, hope that helps.